Okay, welcome everybody to this workshop on Mode 2 interlaminar fracture toughness. We have had several workshops. First, a series of 6 related to the strength of composites, where we first tried to define strength, and then we went into tensile, compression, shear strength, transverse strength, and also trying to link that to multi-directional composite strength. Now, more recently, we have started a series on fracture toughness. We first asked whether toughness is a material parameter to start with, which is not an easy thing to come to an agreement on. About a year ago, we had one on mode 1 interlaminar toughness. And so today we are continuing with mode 2 interlaminar toughness. And we have already agreed more or less between the 3 of us on the next topics, which would be a combined session on mode 3 and mixed mode interlaminar toughness. Then one on interlaminar fatigue, covering in principle all 3 modes. And finally then translaminar toughness, which we have not touched upon yet. Just for the people who are not aware of these, or is the first workshop that you attend, we want to raise awareness of the difficulties, especially the practical difficulties in measuring these properties, in performing these tests, help the community in general try to identify best practices. What should we be doing differently? What should we try to agree on to do it a certain way or not to do it a certain way? And in some cases also identify the next steps. What should we try and research to better understand or to be able to do better tests for toughness in this case, or for strength in the previous series? Brief overview of the agenda. We will start off with the presentation of our 1 or 2-page paper by Michael after I finish. Then we will have 7 5-minute presentations. We'll first have a short discussion among the panel members for about 20 minutes. Then we'll probably have a short break, and then we also open the floor for questions from the audience, which you can do via the Q&A, or you can raise your hands. Then we allow you to unmute yourself, and then you can ask the question orally to the panel members. And then we have about 20 minutes at the end for conclusions and suggestions for next steps. And that will be the end of the meeting in 3 hours at the very latest, maybe a little bit earlier, depending on how many discussions we have. The overview of the 5-minute presentation, they were also in the invite. We've tried to arrange them a bit in a logical order. This is the order we'll actually be following. I will not read them off. You've also seen them in the invitation email. To conclude, I want to give you a few ground rules. We are recording this session, so if you unmute, whatever you say will be recorded, also for presenters, of course. We will share the slides and, of course, the recording afterwards. All our previous workshops can be found on YouTube if you're interested to watch one of them again. And the same will apply to this one. During the discussions, you can write questions in Q&A or raise your hand. You can, in principle, do this anytime, but we will only get to actually answering the questions after all the 5-minute presentations and after we've had the short discussion among the panel members. If we get a lot of questions, it can be useful if you can upvote questions that you were also about to ask that you're particularly interested in. That helps me to screen a little bit which ones go first. We unfortunately cannot have cameras for the audience. This is a limitation of the Zoom environment. If you want to just say hello to a colleague, you can use the chat for general comments. And I think you should also have the option to chat directly with one of the participants, although I'm not 100% sure about that. Another limitation of the Zoom webinar we do is the participants list is unfortunately not visible. It's only visible to the panelists, so the presenters and the organizers. There's nothing we can do about this in this ecosystem, unfortunately. And with that, I will conclude my introduction and I will pass on to Michael for the presentation of the paper.
Okay, thank you. I'll share my window. Can you see that okay?
Yes, go ahead.
Great. Thank you very much, Yentl, for introductions. And I'm very pleased to give a bit of an overview, a sort of a starting point of a few things, which we will then pick up in some of them in more detail later. So this is really mirroring what we put in the paper, which was available, is available, and will be on the website later as well. So, mode 2 interlaminar fracture toughness and the factors affecting it. Well, first of all, I can get the screen to advance, which it's not doing. Okay. Right. So, mode 2 fracture really is occurring in the resin regions, either between the fibers or between the plies. And you can see this schematic, which illustrates the way that the fracture develops. So you start off with deformation due to shear and matrix plasticity, and then tensile cracks typically form at around 45 degrees along the direction of the maximum principal stress. And then as deformation continues, these cracks extend and they distort into sigmoidal microcracks, which eventually coalesce and form a macroscopic crack. So one of the questions here is, since the failure really initiates in tension, is it really shear failure at all? And Kevin O'Brien wrote a provocatively titled paper some years ago, Composites Interlaminar Shear Fracture Toughness, G2C, Shear Measurement or Shear Myth? And it is an interesting question because it depends a bit on the level at which you look at the deformation and the fracture. And another point, which is perhaps related, is that at the very beginning, then when at the start of the crack, because the shear stress has to go to zero, then initially it must really be mode 1. So it's perhaps more of a philosophical point, but it's still an interesting point perhaps to debate. The most common method for measuring G2C is the end-notch flexure test, which has been standardized, ASTM standard, and it's a good test, widely used. One of the problems with it is unstable, so it only generates an initial value of the initiation toughness. There are a number of potential complications with the test, and quite a few of these are discussed in the standard. One particular important issue is the effect of the insert, and normally you will do an initial test from the insert film to generate a true pre-crack in order to do the main test. And this normally gives a lower and more conservative value than if you just take the initiation from the film. So, some of the issues with measurements. One of the things with mode 2 is that the process zones can be very large, several millimeters in some cases, even more potentially where there's adhesives and very ductile materials. So it can be very difficult to actually define what is the crack and how to accurately measure it. It's very hard to determine it visually, partly because of the ambiguity about the way it develops, partly because of the very limited crack opening in mode 2, and also the crack front is not necessarily straight, so if you observe on the edge of the specimen, you're not necessarily getting the true averaged crack length. So for these reasons, it's usual to determine the crack length from the compliance. There are a number of different data reduction methods which have their pluses and minuses, and that's another area of discussion. So what about resistance curves? If we want to get beyond the initiation value, then we can get stable delamination by using a 4-point bend rather than the 3-point bend of the ENF test. And there are some concerns with this test, particularly with regard to increased friction. And as a result of that, there's an alternative stable configuration, which is the end-loaded split. And that test has shown with work by our presenter Bamber Blackman and others that tends to not give a very large R curve, although he may show us some results later which might contradict that statement, and that could be an interesting point for discussion later. So is GC really a fixed value? Is it a material parameter? Well, there's been a number of things which have been demonstrated to affect G2C. One thing in particular is if there's through thickness compression, it can make a huge difference. So some tests that we did a while back where we used a specimen with a cut center ply loaded in tension, and this delaminates along the interface between the cut and the continuous plies under mode 2. And by putting a transverse loading on it, we could see how the G2C increases with transverse compression. And it's a very big effect. So you see that this, even with about 10 or 15 megapascals, the effect of G2C has doubled. So this is a very major effect. Also, going back to some work we did many years ago with these same sort of cut ply specimens, we found that when we scaled the specimen and had specimens with different sized cut plies, then the GC value actually increased with specimen size. So that raises issues with regard to scaling effects and whether we can really consider this as a fixed material parameter. When we go on to look at multi-directional laminates, the situation gets more complex. The damage is very complicated. We have problems with migration, and it's really quite difficult to avoid the delamination migrating in multi-directional composites. When tests are done with multi-directional materials, then typically we do see higher G2C values as the angle between the different plies increases. And you can see some data on the right here for different interfaces, with the unidirectional specimen giving a lower bound and the other ones giving higher values because of the additional complexities of the damage and potentially migration issues. But using the unidirectional ones ideally should be conservative. Environmental effects can also make a big difference. So this work from Leif Asp on the right shows that G2C reduces with both increasing temperature and with moisture. You can see that both for the dry specimens and for the wet specimens, there's a reduction with temperature, with the wet ones being below the dry ones. That's not what's been reported for all materials, and in some cases there may be conflicting trends, because whilst increased plasticity with temperature may increase the fracture toughness, then sometimes we see that that moisture in particular can reduce the interfacial strength, and this may adversely affect the fracture toughness. Effective strain rate is also very difficult to determine, as Michael will tell us a little bit later in his presentation. So there's some references. These are all what's in the paper. So that concludes my brief overview introducing the topic. And now we'll move on to the more detailed presentations about some particular aspects. So I'm now going to stop sharing my screen.
Okay, thank you, Michael. Then we first move to Bamber Blackman. You can try sharing your screen, Bamber.
Okay, thank you. Okay, has that come up? And can everyone hear me?
Yes.
Okay, well, thank you for the invitation to take part in this very interesting discussion this afternoon. I'm going to be talking about the validity of mode 2 fracture toughness measurements in composites and joints. So this is some of the work that I've been involved with at Imperial, and also I've been involved with through the European Structural Integrity Society ESIS TC4 group. I'm going to say briefly about some historical perspective and development of one of the standards that Michael referred to, the ISO 15114, which is the ELS method, where this works and where some problems lie, and what might be some possible solutions. So to provide a bit of historical context, the European Structural Integrity Society Technical Committee 4 on Polymers, Composites and Adhesives has been working on mode 2 delamination since very early days of its existence, which takes us back to the mid-1980s. Due to the desire to measure the resistance to crack initiation and propagation, the committee always favoured the ELS method over the less stable ENF that Michael referred to. However, the early work that we performed within ESIS suffered poor reproducibility between labs, and the versions of the corrected beam theory, which were developed initially by Gordon Williams, didn't accurately reproduce the axial modulus of the composite arms, and the participants all really struggled to measure the crack length. These issues were also identified in the joint ESIS ASTM and JIS round robins of the late 1990s, which were coordinated by VAMAS. And in the first round robin, 3 different methods were compared: the ELS, the ENF, and a stabilized version of the ENF. And the second round robin also considered a 4-point version of that test, which was more stable, and Michael also referred to in a few moments ago. But all methods had limitations, and there was no general consensus. So different committees went their different ways, and ESIS really worked upon developing the ELS method further. So during the development of this particular standard, which appeared in 2014, one big factor was eliminating the effects of the clamp, and the different clamps used by different labs, because they weren't standardized, it did introduce certainly variations in compliance, which had to be taken into account. And the other major problem experimentally was what to do about measuring the crack length. And it was one of these situations that the closer you looked at a mode 2 crack, then the more confusing matters became. And you saw this micro cracked region, as Michael also referred to, and what you call the crack length was really tricky to define. So we moved to an effective crack length approach in the development of this particular standard. Looking at the reproducibility that we obtained, then certainly we always defined initiation via the 5% offset, rather than from the initial film non-linear point. And mean propagation does depend a little bit on whether you have flat resistance curves or rising resistance curves. But for the composite that we used to develop the standard and run the round robin, which was IM 7977-2, we measured relatively flat R curves. So looking at the different analysis methods, we found the analysis method that didn't involve the measured crack length, which we described as the CBTE, or corrected beam theory with effective crack length, gave us the lowest coefficients of variation and the best reproducibility. So we found the results reasonably good for composites. We then went on and used these techniques for structural adhesives, and we ran into more significant problems. The larger toughness and the greater ductility tended to give us relatively strong rising R curves, and the force displacement and G value, resistance curve you see here is for a relatively low toughness adhesive with a G1C value of around about 1 kilojoule per square meter, rising to about 5 kilojoule per square meter in mode 2. However, really things didn't work well with even tougher adhesives. And this adhesive has a mode 1 toughness of about 3 kilojoules, and you can see didn't reach a steady state in our test. You can see continually rising R curves. So one has a problem with applying the methodology to these sort of systems. More recently, we've used DIC techniques to try and get a better handle on what's happening with these very long damage zones. And certainly DIC can show the extent of the damage in the adhesive layer, and obviously gives us the opportunity to measure G and J simultaneously, which gives us the option to compare G and J, which can be very revealing. And the other thing that this gives us the opportunity to do is to observe and identify delocalized damage in the sample, which we were otherwise unaware of. So by careful selection of the contour integrals with these sort of approaches, you can exclude localized damage. And we found that the G and the J revealed that the G were influenced by non-localized damage in this sort of specimen. So obviously possible solutions to these problems where you have ductility and a lot of toughness in the system, you could move to larger specimens. For adhesive joints, you might have specimens from anything from 200 millimeters long up to 1 meter long. And there's data in the literature where 1 meter length joints have been tested, not by us, incidentally. And of course, measuring G and J simultaneously via DIC methods is also a very promising way forward. So I'd just like to finish by acknowledging members of the ESIS TC4 committee here, and look forward to the discussions and other presentations this afternoon. So thank you very much.
Thank you, Bamber. Yeah, we will not have questions in between the short presentation. We immediately move to James Radcliffe from NASA now.
Good afternoon or good morning for those like me on the other side of the Atlantic. Okay, bear with me. Okay, can you see my title slide?
Yeah, go ahead.
Okay, great. Thank you. So my colleague Nelson Cavallo and I, several years ago, were dealing with attempting to measure in Mode 2 interlaminar fracture toughness of an interface between a fabric layer and a tape layer. So this is the scenario we were faced with. So this is basically a situation where we were doing some validation test methodology development, whereby we're recording detailed damage progression, initiation and progression in coupons or components like this hat stiffened panel that you see depicted here. And then one of the issues for the lower building block requirements was to generate fracture toughness values for the interface where we knew delamination was going to occur, in this case between the interface between a fabric layer and a tape layer. And so what we, it didn't take long to discuss the situation pertaining basically what Michael and Bamber has just been discussing, which is the issue really of what's going on when you're applying a pure shear Mode 2 loading to a laminate. In the cases that we're traditionally used to seeing when we're attempting to standardize a material property measurement, you have a situation like we're illustrating on the left here, where regardless of the sign of the stress state, you'll get some situation similar to what Michael was depicting, and you should be able to obtain a unique interlaminar fracture toughness. So then the issue is, well, what happens then now when you've got dissimilar material interface? So in this case, tape ply on the top, fabric ply on the bottom on the left-hand side. So if you can imagine either if you flip the material direction, or rather orientation, or the stress, or change the sign of the stress state, then these local Mode 1 driven cracks that Michael was talking about are either going to be driven towards the tape ply or going to be driven towards the fabric ply. So in that case, do we have a unique fracture toughness? And that was just a simple question that we wanted to ask. And I guess you can probably figure the answer. So this is a racehorse commentary through what we found. So what we did first of all was just to put together a very basic stacking sequence for a specimen using the Bamber's and the ISIS standard. And what we did was the following: we just basically took a sublaminate, which was a sandwich of a fabric and tape plies, where the core of the sandwich is a series of tape, 0 degree laid up tape plies. In this case, it's 7 on the top, not 6, it's depicted here. And then the skins of the sandwich are fabrics. And then there's another sublaminate where we just extract 2 of the tape plies and just put them on the other side of the fabric, and then we bond those two. We cure those 2 sublaminates together as a single laminate. So we end up with a laminate that has minimal mechanical coupling and any influence on thermally induced residual stresses. And so we use this configuration in a CELS fashion to then measure the apparent Mode 2 interlaminar fracture toughness. So I'll cut straight to the results. We found that when we were loading the specimen such that these Mode 1 local microcracks were driven towards the fabric ply, we developed a significant R curve, as you can see by the open circles on the chart on the right-hand side. And then if we changed in the same specimen or a specimen taken from the same plate, if we reversed the loading, or rather had the specimen oriented in the CELS fixture such that the local microcracking is driven towards the tape ply, we get some stable crack growth followed by some instability. But we managed to measure apparent initiation toughness of both situations, and then some propagation for both situations. And so we see the steady state the initiation fracture toughness when we're activating or driving the cracks toward the tape ply is significantly less than when we're activating the damage to be driven towards the fabric ply. And that situation is even more significant if you look at steady state. So in this case, if we were we're assuming, at least in the case of driving the crack towards the fabric ply, we've got steady state after about half an inch of growth. So if you take the average of those data, that's the average value shown in the table at the bottom left there, compared to the average propagation value from the tape-driven situation. So we see clearly there is no apparent unique fracture toughness depending upon the orientation and stress state. So we wanted just to sort of confirm what really the situation is locally. So the micrograph here, what you're seeing is you're looking head on, widthwise in the specimen from left to right. Crack growth is coming from out of the page towards you. And so this is a depiction of a laminate just ahead in the crack propagation zone, where the local microcracking is driven towards the tape line. So you can see the fibers which are coming out of the page, and so you have a very clean looking fracture surface. Conversely, when you look at the situation where we then took a specimen and drove the microcracking towards the fabric ply, you see something very different. So now you've got cracking that's gone both sides of the toes, and there's clearly a more arduous crack path that constitutes macroscopically what we're observing to be interlaminar fracture. So clearly there are local mechanisms that would result in this non-unique fracture toughness of the same panel. So that's basically the conclusion here, is that not only is actually trying to measure interlaminar mode 2 interlaminar fracture toughness a challenge when you have a plate of a given material, then when you try to extend that to situations where you actually want to measure interlaminar fracture toughness of an interface between similar materials, then you've got this additional challenge that you don't have a unique fracture toughness, because now we have a situation where now the relative orientation of the stress states to the orientation of the material comes into play and has a potentially significant influence on the apparent mode 2 interlaminar fracture toughness. And that's it. Thanks very much. Thanks, Michael.
Thank you. Then we move to our third presenter, which is going to be Yu Gong.
Okay. Can you hear me?
Yes. And we see your screen. You can start.
Okay. Okay. Good afternoon, everyone. I'm Yu Gong from Chongqing University. Thanks for the invitation from Professor Michael Wislom. Today, I would like to share with you our work on a semi-analytical method for determining mode 2 fracture toughness and traction sublation relation. Our goal is to develop a method that can be applied across. Across the major experiment method for mode 2 delamination, including the end-notched fracture, end-loaded split over notched fracture, ballpoint end-loaded fracture testers. Researchers have experimentally measured the mode 2 fracture toughness curve, which is mainly resulted by bridging and matrix plastic deformation to utilize the performance potential of composites. Fracture toughness curve should be determined to achieve accurate evaluation on the delamination damage. Most current test methods require accurate measurement of the delamination length. However, the monitoring of mode 2 delamination is considered to be a difficult task due to the delamination growth without a clear opening, and as a result, direct observation of delamination length is tedious and the source of uncertainty. Moreover, in order to extract the traction sublation relation, observing the relative sliding displacement at the pre-crack tip in mode 2 is necessary, which is even more challenging. Avoiding those difficulties is the central motivation for developing the semi-analytical method proposed here. We also noticed that many existing data reduction methods require to measure the specimen's elastic constants. In addition, friction and geometrical nonlinearity can affect the fracture toughness measured from different test configurations. So although researchers have proposed approaches that avoid the measurement of occurrence, they still struggle to balance operational convenience in experiments with the simplicity in data processing. For example, Perz-Garmer's proposed a closed-form solution based on the J-integral for mode 2 delamination, but it requires additional measurement of the rotation at the loading points to other representative methods in the actual elastic parameters. And because the compliance formulas involve too many unknowns, it's difficult to derive the traction-separation relation. So our goal is to develop a semi-analytical method that does not require measuring elastic constants or monitoring occurrence in real time, yet can determine both fracture toughness and traction separation relation. So in this slide, I briefly outline the proposed method. Because the stress field at the mode 2 occurrence is complex, we apply the Angerser-Castigliano theorem to calculate the displacements at the loading points, and then establish the relation between specimen compliance and occurrence. By substituting the initial occurrence and the compliance, together with the occurrence and the compliance obtained upon unloading, we can solve for the specimen bending and the shearing modeling. Then the occurrence and the fracture toughness can be obtained. Next, a unit load theorem gives the relative sliding displacement at the pre-crack tip, enabling determination of traction separation relation based on J-integral method. It's worth noting that in our derivation for over-notched fracture and 4-point end-notched fracture testers, a point friction model is introduced to account for friction effect. So the semi-analytical method likewise yields accurate results. And to verify its applicability, we prepared laminates with various stacking sequence and material types. The following two slides demonstrate the accuracy of the semi-analytical method in determining fracture toughness and traction separation relation. The calculated results match the experiment data closely. We have also performed numerical validation using a trilinear cohesive zone model. Taking the over-notched fracture test, for example, the simulated response also agrees well with the experimental loaded displacement curve. This further confirming the method's applicability. So that's all. Thank you.
Thank you, Yu. Then we go to our next presenter, which is Michael May.
Good afternoon, everyone, and I hope you can hear me well.
Yes.
Okay, so my team and I have been working on the measurement of high rate properties of composite materials for the last good 10 years, and one particular test where we encountered specific challenges is when we want to test the mode 2 fracture toughness under these high rate loading conditions. So why are we actually interested in measuring this? Because in principle, what you see is if you have a polymer-based material, the faster you pull at it, the higher you will have higher will be yield stress, higher will be failure stress, but you will also see some sort of embrittlement. As when we're talking about polymer matrix composites, the matrix is polymer. We will have properties which are strain rate dependent if we load the composite under conditions where the matrix is dominant, for example, for shear. So for simple plus minus 45 shear test, we see that. The question is, do we also see that for the mode 2 fracture toughness if we increase the loading rate? And this is a very nice chart, which is coming from a very recent review paper coming out of Oxford, which shows normalized mode 2 fracture toughness for many different sources over a wide range of loading rates. And the answer that we have to this question, do we actually see a rate effect, is I don't know. Because when you're looking at this vast amount of data, there seems to be a trend which increases, but we also see very large error bars. And what we also observe is that many of the people doing these tests, there's nothing like a standard. Everyone uses different ways of testing, and each of these tests have their own benefits and their own drawbacks. And so it's really hard to compare these types of tests. So one of those challenges where it's also hard to compare what people are actually measuring is that there are simple things like, how do we actually define the loading rate in the mode 2? In some sources of literature, people just give the velocity of the test machine. Is this relevant? Maybe not. Some give the strain rate of the specimen, but depending on the loading condition, what is the strain rate and where do we actually measure it? Could it potentially be the shear rate at the crack tip? And once again, how do we measure it? Or is it maybe the crack velocity? Then when we're doing the actual measurements, we are facing a few challenges just coming from the experimental setups. On the one hand, we may face inertia effects. We may face oscillations in the load signals, in particular when you're working with servo hydraulic test machines. Tracking the cracks is quite hard under static condition already, as we heard. It's even worse when we're going dynamic, when cracks are propagating at higher velocities. Sometimes we have asymmetric specimens, and we have localized stress peaks within the specimen. And all of this really poses big challenges to actually doing a proper, well-defined mode 2 fracture toughness test. So what are the methods on how we can actually achieve fast loading of specimen? And there are three main categories of machines that we can use. We can either use a servo hydraulic test machine, we could use drop tower, or we could use a split Hopkinson bar. So the servo hydraulic test machine has the advantage that we can test to very large displacements. We have a more or less constant test velocity. However, we see that very often those load signals that are coming out of these machines are oscillating, so the force measurements are not very good. For the drop tower, we can sort of achieve large displacements, but the test velocity is not constant at all. And also here we see lots of oscillations in the load signals. The split Hopkinson bar, which we prefer to use at EMI, has the advantage that we have very little oscillations on the load signals, so force measurements are good. Test velocity is okay. However, we cannot achieve large displacements for such test. Then, looking at different types of specimens, I think they have all been mentioned before, the end-notch flexure test, end-loaded split test, or the TCT test. They have all been widely used under static conditions. So what happens if you want to take them to dynamic? So for the ENF, there's a standardized data reduction scheme. This is positive. However, like for the static, we suffer that we have unstable crack growth. And in particular, under high rate loading conditions, I'm personally not a big fan of loading specimens in bending because I'm not quite sure where all of the waves are bouncing back and forth, which is making things probably rather dubious. Similar for the end-loaded split, here we have the advantage that we have a stable crack growth, we have standardized data reduction, we don't need to measure the crack length, which is an advantage under dynamic conditions. However, it's a complex test fixture, test is unsymmetric, which poses additional challenges under the high rate conditions. The TCT test that Michael mentioned earlier, the advantage is it's a simple tensor test. we only need to measure the maximum force. So for the Hopkinson bar, if we have a good measure of the maximum force, this is good. However, it is well away from being standardized, and as Michael also showed, the through thickness stresses may affect the fracture toughness. Nevertheless, we went and tried to see what we can achieve with this TCT test. In this particular way, we used the modified TCT test coming out of a paper by Scarici. And we put that into our Hopkinson bar. So we have special mountings which ensure that we have constant impedance going from the bars to the specimen, looking at it with a high-speed camera. And what we found was that under quasi-static conditions, and this was the first issue for us, the fracture toughness that we extracted for the TCT was about 27% higher than for the ENF. However, what was nice is we scaled the length of the TCT, and for our case, for the high rate, the big TCT and the scaled down TCT showed similar test results, and we saw that the fracture toughness increased by about 60% when we increased the loading rate. Challenges that are still to be answered is what do we do with the through thickness stresses? And one big challenge is we have those 4 cracks, and in most of experiments, they did not all start to propagate at the same time. Sometimes it was just 1, sometimes it was 2, and I don't think we had a case where all 4 of them were actually propagating. So there's further work needed here to get this test working. And that's all from me.
Thank you. Then we move on to our 5th presenter, which is Giuliano Allegri.
Thank you. I'll immediately share my screen. Can you see my screen?
Yes.
Okay, oh, sorry. I was actually... so I would like to present what I call an entropy-based perspective on fracture toughness, but really, I mean, my personal view is that Kevin O'Brien is absolutely right, and as a matter of fact, mode 2 fracture toughness does not exist. It's a quantity that we try to define based on say engineering applications, but in reality it's the byproduct of complex processes which are heavily influenced by all the factors that have been discussed so far, including rate, but also environmental conditions such as temperature and moisture. So what we've been doing as work at the University of Bristol, we are mainly interested in the modeling side of things, but with a clear, say, strategy towards validated models that can be compared with good quality experimental tests. So our strategy for modeling, let's say, mode 2 delamination is based on a thermodynamic approach where essentially we recognize that the failure occurring in mode 2 is governed by a certain set of dissipative processes, and in order to model rate and temperature effects, we consider the matrix to be viscoelastic, whatever matrix means in this context. And essentially, what we do is to determine failure by essentially prescribing a damage evolution law, which essentially accounts for the entropy generation rate during the progressive damage process. You could say, well, what's new about this? Everybody uses traction displacement laws. Okay, first of all, the linear part of the law is a generalized Maxwell model, nothing particularly new here. But for the traction separation law, we do not prescribe the shape of the law at all. What we prescribe is essentially a damage evolution equation, which is the general form of a Paris law, where, sorry, a power law, not a Paris law, where we have a prefactor that is temperature and time dependent, and it essentially obeys the Zurkov kinetic strength theory of solids. And all of this has been implemented in a Abacus VUMAT. We typically use explicit analysis for our models, as Michael knows very well. So how do we use this? Essentially, we, as part of an Innovate UK program called Fantastical, we were essentially tasked to build models that could capture the influence of rate, temperature, and moisture on the fracture of CFRP. So we carried out a very large number of tests at different rate, temperatures, different mode conditions, but essentially what I'm presenting here are the ELS-based tests that we performed. We didn't try to extract a fracture toughness from these tests. We looked at the load displacement curves that we get from the tests, modeling, the coupons with the solid elements for the sublaminates, and just sticking a cohesive zone plane with interface elements between the two sublaminates. And then we have essentially calibrated the model that I've shown you in the previous slides on a single case, testing at room temperature at 1 millimeter per minute. And we were essentially able to fit with a single set of parameters all the experimental load displacement curves, considering three different rates, ranging from 0.1 millimeter per minute to 100 millimeter per minute. And we were able to capture also interesting effects, such as the experimentally observed instability of the lamination growth in ELS coupons at minus 55 degrees. So we didn't try to measure the fracture toughness. We effectively considered the ELS coupons as representative coupons where there is a single interface failing in mode 2, without actually trying to look into the mechanics of the interface, but capturing the underlying processes with a damage evolution rate equation. And this approach has also been extended to mode 1 and mixed mode, so it works reasonably well. I cannot tell you specifically what this material is, but let me say that it is a CFRP system with the thermoplastic interleaves. And this is all I have to say.
Thank you, Giuliano. Then we have two presenters left. The next one will be Faustino Mujica.
Good afternoon, everyone. I'm Faustino Mujica from the University of the Basque Country in Spain. My presentation is related to the material specimens. Okay, when the upper arm is stiffer, we have no contact between both cracked arms, and there is a concentrated force at the A support, at the left support, and the main effects are due to bending effects, due to flexure compliance effects. The conditions of pure mode 2 are related to the new normal stresses at the interface between both crack arms in the non-crack zone between the crack tip and the force application. Applying the condition, we get that the wave force is equal to the shear force in this zone, and then we get the condition for pure mode that is the same in mode 2 and in mode 1. This is a related publication. In pure mode 2, in the non-crack part, the sections of rotation is the same in both arms. The lines, the sections are plain in the hull beam, and there is it can be created or analyzed like a sample beam. The energy release rate is determined by the energy or complementary energy, and we use the concept of the equivalent crack length that depends in the compliance and the elastic properties of the specimen, and that includes all the effects that affect the compliance, including the factor process zone. Here we have a zone of damaged material, the new model in finite elements with the cohesive zone, and in our case, this zone is modeled based on beam theory, like an equivalent crack length that incorporates all effects that take part in the compliance of the specimen. The energy release rate is determined based on the elastic properties and on the equivalent crack length, and the results obtained are the same as those based on the rotator angles in load and reaction sections. And the experimental data needed for this analysis are only load and displacement of the load, of the usual load displacement curve of the test. With respect to some numerical results concerning small fracture process zones related to linear elastic fracture mechanics, we calculate the energy release rate by two ways. In a global way, taking into account the applied force and the displacement of the application point, and by VCCT, the crack tip, and the results by VCCT are the mode mixity is near 100, that you can see in the slide. With the global method, by FEM also, we have similar results, and the difference are up to 2%. And with the analytical approach, we have results that differ a maximum of 3% with respect to the global results. With respect to the relevance of the use of the equivalent crack length, we define the visual crack length in a finite element method as the last linked node, and this last linked node advances when a node separates, but as the FP set is advancing, the equivalent crack length varies depending as a function of compliance and elastic properties. And the energy release rate is first determined by as a G integral by the integration of the fraction separation law. These are the results. And analytically, we determine the energy release rate by two ways. The first way by the visual crack length. You can see the results, and by the equivalent crack length. And in this second case, the agreement occurs when the equivalent crack length is used. With respect to sensitivity, with respect to geometric and elastic parameters, we have some uncertainties in dimensions and in elastic properties, and we run a Monte Carlo simulation with 10,000 iterations. We have here the equivalent crack length, the initial values, the mean values that match the initial values and the standard deviations, and the energy release rate in mode 2, the initial value, the mean value that match the former ones, and a sum of the last one with the standard deviation values. With respect to the statistical values, at the point of maximum standard deviation of G2, we have these values of coefficient of variation that show that the analysis is stable with respect to the uncertainties. But if we assume in some way that the values of A are accurate, the curious fact is that the coefficient of variation is greater in the case of this accurate value of A than in the previous case. That's all. Thank you very much.
Thank you, Faustino. Then we move to the final presentation from Alberto Barroso.
Right, let me put the... One second. Can you see my screen?
Yes.
All right. Well, good afternoon. Thank you, Michael, Federico, and Gentle, for inviting me to this workshop. My name is Alberto, and I will briefly present some issues found during Mode 2 testing in this Cerbon project you see on the screen. Let me just 30 seconds to introduce you the big picture of this project. One of the things we did in the project was a round-robin test for Mode 1 static and fatigue characterization of co-occurred panels. We also made a round-robin test for Mode 2 static and fatigue characterization of the same co-occurred panels, of course, other panels, not the first one, with a final objective. It was failure predictions under static and fatigue loadings on adhesive single lap joints, which typically have this mixed mode loading. So I will only focus on the topic of this workshop, is the things we found and the issues we found during the project. So we had 5 participants were involved in this part of the project with testing and numerical prediction. As already introduced in the paper prepared by Michael, Federico, and Gentle for this workshop, we basically have 2 standards to work. In the project, by its simplicity and only for initiation, we choose ASTM in the round-robin program. In any case, it is remarkable that the ISO standard indicates that ASTM might have larger errors due to friction than the ISO standard. So it's something to take into account. All the manufacturing of the samples was controlled at our group in the university, so we have control of all the samples and delivery. And although you are familiar with the standard itself, I think it's important to quickly summarize some issues and the procedure, because we have the things we have found and can be useful for the final discussion of this workshop are related with parts of the standard we do not fully understand. In our case, a laminate with an adhesive layer in the middle is prepared with an insert. The test is basically a 3-point bending with a crack length defined by the distance between the roller and the end of the insert. So you apply the load, measure the displacement, and you have to measure the compliance of the sample in the straight path of the curve, as the standard says. You have to measure 2 compliance tests using 20 millimeters and 40 millimeters as the crack length in what the standard defines as the non-pre-crack configuration, only with the insert, and only loading up to 50% of the estimated maximum load. Then a fracture test is carried out using a crack length of 30 millimeters until a visible crack advance appears or a significant load drop takes place. In this situation, we have what the standard defines the pre-crack configuration, and then you have to repeat the three tests for this configuration. In that case, the compliances are plotted against the crack length to the power of 3, make a linear fit, and obtain these parameters, the slope and the initial value, because the slope participates in the definition of what the standard defines as the toughness candidate. And after some validations and verifications, this candidate is converted into the mode 2 toughness. So with all this in mind, these are the results we have at the moment, with only 3 laboratories participating. The first issue is clear. You can see here that one participant showed much higher failure loads in 4 of the 6 specimens. These results had no explanation at all and were discarded. So the second issue is be careful if you use automatic already predefined testing programs, because one of the samples of one of the participants showed an increasing resistant behavior after the first crack advance. This is not usual, but in any case, it's not valid. An automatic load drop criteria of these programs should be taken with care. An additional issue, which from my point of view is not minor, is that this may be one of the most time-demanding quasi-static testing for a standard testing. So one loading and unloading may take 6 minutes. Each sample, if you follow the standard, has 6 loading and unloadings, which makes at least 36 minutes. And if you have 6 or 7 samples, this takes 4 or 5 hours just for testing, not for white painting, marking, post-processing results, and that's all. So the results we have for the laboratories with valid results are the one you see on the screen. The first thing is thing which is obvious, is that with something which is already addressed in the workshop paper, is that the mode 2 toughness for the pre-crack configuration is lower than the mode 2 toughness of the non-pre-crack configuration. I guess the crack is sharper than the insert tip at the micro scale, so that's the reason. A second issue is that we haven't found a clear trend for the results scattering. While one participant has obtained much higher scattering in the non-pre-crack configuration, the other has just the opposite, the contrary. So I would like also to know about your experience in this point. Please remember that we are dealing with cured samples and not with true interlaminar toughness configurations. And the third one, due to the excessive time consuming associated with this test, we have serious doubts about the necessity of recording all unloadings as the standard requires. We think that the only necessary unloading to record is the fracture test with the crack length of 30 millimeters of the non-pre-crack configuration, because it allows you to measure the crack length using the compliance of the new pre-crack configuration. So that's all from my side. Thank you.
Thank you. So now we will have a bit of time first for discussions among the panel members before we have a short break and then open it to the audience members. Who among the panel members wants to kick it off?
Perhaps I'll ask the first question, if I may. Bamba, you showed some very interesting results about the R curves. And I'd just like to ask you a bit about the mechanism for the R curves. Is this due to the increasing process zone size, or what is causing that very large increase in toughness that you showed for some of those specimens?
Okay, yeah, thanks for the question. So the big increases in fracture resistance were seen with the more ductile systems. So these were the joints. So both of those systems were adhesively bonded. So the cracks growing through the adhesive layer, sort of cohesively, sometimes close to the interface, but within that layer. And what appears to be happening is the length of the process zone seems to be increasing. So in that early part of the load displacement trace, where it's still rising, the crack is growing, but additionally the process zone is growing too. But they're not growing uniformly. So it takes until the plateau region for the two to be moving together sort of in a self-similar manner. So interestingly, for the tougher adhesive, the length of that process zone is really quite large. We think it can actually involve the entire uncracked part of the adhesive joint. So you can see that we had some feeling that that was happening, but you really need something like DIC to be able to see just how far in advance the adhesive layer is deforming. So that seems to be what's happening. It's the increase in the process zone size.
So, well, that's very interesting if they really get so large. And I guess that raises the question about how this could be used. You know, if you've got such a big effect, what's the appropriate value for people to try and use in design or analyzing structures? Would you have any comments on that?
Yes. So, well, certainly we would be looking to use the steady state value in these cases. So obviously, whilst I mean, in principle, I mean the resistance curves seem to initiate at around about the mode 1 value. We see that reasonably consistently, and then they rise rapidly. So when self-similar crack growth develops, we're obviously on a on a situation where the damage zone, the process zone, is being driven forward. So that would be an upper bound. So you could argue there that, well, actually, what do you want in a structure? Do you want to know when it initiates, or do you want to know how it propagates? So yeah, there's some definitely debate over which value to take in those cases.
Thank you very much.
Other questions?
Yeah. Could I ask a question? Yeah. So well, I always like asking questions to non-believers. So Giuliano, could I ask a question? So clearly you're a mode 2 non-believer, which is fine. There are many around, so my question really is, I mean, I think I agree that mode 2 invokes many complex mechanisms, and what you're saying is that you think you can model predictively the individual mechanisms. So okay, you shook your head. So would you say that we therefore don't need a mode 2 test? Would you be confident to be able to model the fracture resistance independently from, blind from an experiment? Or are you saying that, no, we need a test, but I can't explain the results?
So I was being deliberately provocative. So it's not that I'm a non-believer. It's that, whenever we talk to industry, we have so many questions asked from them, and that is, what happens with the rate? What happens if my test becomes unstable when I go up with the rate, which I remember, Bamber, you showing a few years ago. So which value do we extract? Which value do we use? And, our answer is first of all, we need to see how we are using fracture toughness at structural scale. So we want a value of the fracture toughness, and then we use, I don't know, a cohesive zone approach, bilinear, trilinear, whatever, or a VCCT technique, and we use that value of fracture toughness. Okay. That doesn't work in all the cases. It has to be tailored to the specific case. If you have a stick slip mechanism, it doesn't work. So we tried to factor those effects in our models. And essentially what we did, there is a slide that can be illustrative from this point of view. So effectively, we do not prescribe a cohesive law. This is the cohesive law that we get as the elements, are loaded in shear and then fail during the analysis. And it's different depending on the rate, is different depending on the temperature at a given rate. It would be very interesting to compare this with the results that that were shown before about, you know, the determination of individual traction displacement laws. But essentially, we were looking for a solution where we are aware that we cannot capture the micromechanics of mode 2 delamination growth. We are aware that the micromechanics is influenced by all these parameters, and so we were trying to devise an approach that captures at the mesoscale the underlying physics and can make sense of these effects with a single set of parameters. Clearly, this is a model that fails if you try this model on a multidirectional laminate where you have a mode 2 crack that perhaps migrates, or a bridging zone for a mode 2 crack that essentially involves multiple plies fracturing through the thickness. Well, this approach will not work because this approach has been, essentially calibrated on the case of a single crack growing along a plane. We have actually used it for, cases of more complex mode 2 propagation where we have cracks bridged by multiple plies fracturing, but we had to insert the splits also in between, so intralaminar splits to model these effects. So it's not that I am a non-believer, it's that I am I would say, very conscious and troubled of the questions asked by industry.
Are you happy with that answer?
Yes, that's fine.
This is James. Can I add to it?
Yes.
Yeah. So there's a theme, and I'm biased because of what I presented, but there's a theme that I don't hear discussed a lot often, which is the relative orientation of stress state to material direction. So there was so obviously lots of work done, and some presented this morning or this afternoon with respect to attempting to measure interlaminar mode 2 fracture toughness of multi-directional laminates, or delamination at a non-zero degree ply interface. And you could argue that you need a certain relative orientation of in terms of tape of fiber direction and stress states to permit the mechanism, the basic principles that Kevin discussed and Mike illustrated this morning to occur to enable an interlaminar crack to exist. Otherwise, you're going to kink out of plane and it's going to be something else. So I think for us, we struggle a little bit with this idea that there is a unique value, since in reality, the chances are you're either going to have damage forming at an interface between, plus and minus theta degree plies, and then you've got the relative material stress state to worry about, or different materials. So it seems that there are a subset of cases where perhaps in reality, going to Giuliano's question about getting grief from industry, well, one ask for them would be, okay, do you have cases where under shear conditions you see what you think is a mode 2 driven crack, and then go from there, right? And it might be that you've got 0 theta ply interface for a given stress state that does permit that, and then that's what you go tackle. But everything else, it's just something else. So anyway, thanks.
And if I may add to James' point, very often industry do not know what they have in their components, especially components tested at high rates. So they have to go through lengthy fractographic characterizations to understand what kind of the sequence of events and what kind of mode regime was associated to the various events in the sequence.
Yeah. Any further responses to that? Or other questions?
Juliana, can I ask you whether you've compared the integration of your cohesive traction separation with a GC measured with a standard test?
Yes, we did because the first thing that we were asked, I mean, these tests were initially made because the company who was sponsoring us, Rolls-Royce, is not a secret, were interested in having the fracture toughness in all these various scenarios. And so, I mean, you can still, use the standards with the caveat that the standards are strictly speaking valid with a loading rate of 1 millimeter per minute room temperature. In all the other conditions, the standards do not apply, strictly speaking. And then you can compare with, say, a standard bilinear approach or trilinear approach, and you get exactly the same answers. Is the only difference is in the fact that if you use a standard, bilinear or trilinear law, you need to prescribe the fracture toughness a priori. With this approach, you don't, and you don't need to prescribe also a traction displacement law a priori. All these methods, bar the approach that I presented, fail when you have a stick-slip behavior. Because when you have a stick-slip behavior, the crack advances in jumps. So if you prescribe a value of the fracture toughness, which you estimate as, I don't know, a mean between, the peaks and troughs of the load displacement curve, I mean, the FE model is going to give you steady state crack propagation, but that's not feasible. And in problems involving impact, it can be highly misleading.
What about the R curve? Can it capture better the behavior, the R curve behavior? Or maybe you're
There,
seeing R curves for the sort of materials you've been looking at. I don't know.
No, not in there is not much R curve behavior in this specific material because of the way this material is set. But to answer your question, no, I don't think it is able to predict R curve behavior because introducing the R curve behavior would imply having that equation that I've shown be made crack length dependent, which is possible, but we haven't done it.
Okay.
I would actually like to ask a question to Bamber about measuring both G and J. I guess if you do this, you don't get the same values. So if they are different, which one do you believe or which one do you prefer, or how do you decide which one to actually use in practice?
Okay, yeah, nice question. So I think we started to have some suspicion about the G value for one of the tougher systems that we were working with. This was an adhesively bonded joint, and effectively we couldn't stabilize the R curve. So we tried to triangulate upon a G value by mixed mode data and extrapolation. And I think we came to the conclusion that the mode 2 energy release rate was in the order of 17 kilojoule per square meter. Now we worked further on this adhesive, and we used, in fact, we worked with Marie Lisner and the team there at Oxford also on this adhesive. We were looking at the ENF and the ELS, using metallic substrates and using composite substrates. And we both also used the DIC technique and computed J from those results and compared them to G. And what we found for that system, and we were suspicious that the the amount of energy that was being calculated by the G approach was an overestimate. We couldn't exactly put our finger on why it was overestimated. Something was not quite right in the analysis, and what we found with J is that it gives us slightly more versatility in terms of the obviously where we draw the contour integral. And what we found actually is when we excluded the clamped region from the contour integral, we were able to obviously see the effect of this contour selection with J, and we concluded and triangulated on a value of J2 of approximately 11 kilojoule per square meter for this particular adhesive. So that compared to the 17. Now we've repeated this for some other adhesives as well. We've repeated it for relatively brittle epoxies where G and J are very similar, and we've repeated it for sort of more ductile polyurethane systems where G and J are more distinctly different. And so I think we're sort of moving towards an idea where the sort of systems where G is going to be in error and where J will be more appropriate. And obviously this gives us a handle on what we might need to do sort of moving forward with standards, and where the limits of applicability of the standard may lie.
Yeah, I guess introducing a DIC-based method to measure J into a standard is probably not going to happen anytime soon. I think it's probably getting a little bit too complicated for a standard.
We're just within ESIS TC4. We're just beginning to look at that now for mode 1.
Okay.
We came to the conclusion that yes, we could see very good reasons for applying it to mode 2, but we hadn't had any round robins for mode 1. So led by Stefan Malzi in Germany, we're looking at the mode 1 DIC approach. So we're going to see whether there might be a case for getting a protocol together and standardizing that first, but I think mode 2 would be next.
I think James wants to respond to that.
Yeah, so a plug for the other side of the pond. So in the States here, with ASTM D30, we're doing just that. So we have a work item for measuring apparent interfacial fracture, mode 1 interfacial fracture toughness of a bonded composite, and using J, where we have an option either for inclinometers for the necessary load point rotations, or DIC. And there's a subcommittee in ASTM dealing with DIC. So we're ironing out the issues with standardization of the DIC practice calibration and all the practices necessary to ensure that's a appropriate thing to include in the standard. So it's happening our side of the water, and maybe we should talk more, I guess.
Perhaps you could come and join us again for our next meeting.
Yeah, that would be nice.
Okay, any further questions or remarks?
Maybe I have one for James. Concerning the rate effects. So I think it's I've been involved in trying to measure mode 2 delamination resistance as a function of test rate, and I take James's comments how many complexities there are there, and I guess ultimately the problem is we don't really know which way it should go. You talked about in your presentation about most matrix dominating properties improving with rate, and you talked about stiffness and strength. But of course, on the other hand, the ductility decreases significantly, and along with that maybe the toughness. And then we've got thrown into the equation the fact that if you apply the loading rapidly enough, we may actually heat the crack tip. So I think when I see sort of review articles about what mode 2 should do, what the feeling with mode 2 is. I think no one really has any clue, to be honest. And we sort of see a more or less flat line with a potential increase at the highest rates, but that potential increase might be dynamic effects, or it might be adiabatic heating effects at the crack tip. So I'm just going to ask, maybe James, do you have a hunch for which way G2C should go with test rate?
I think you are probably referring to me and not to James.
Sorry, Michael. Yeah, sorry.
Yeah.
Don't worry about it.
Michael, of course.
Yeah, I fully agree with you. There's so many effects which are fighting with each other. Of course, we have got the adiabatic heating, which might result in a reduction of properties. We might have inertia effects, which result in an increase. And what we're currently trying to do, well, hopefully soon trying to do jointly with Girona, is to apply high-speed thermal cameras in order to see whether we see any adiabatic effects at the crack tips, to shed a bit more light onto this. I personally feel that until a certain point, we may have an increase, but when the adiabatic effects become too strong, we will have another decrease afterwards. And maybe there's a zone in between where they cancel each other out, so we might have a plateau in between. But it's actually still some speculation here.
Okay, thank you.
Okay. Unless there is any follow-ups on that discussion, I would actually suggest we take a short break here. There are already 4 questions from the audience. So if the audience has further questions, you can already put them in the chat or in the Q&A, I mean. And then in 10 minutes from now, we will restart again at 20 to 5 here, 20 to 4 in the UK, and whatever time zone you are in. Then we will resume and we'll start answering the questions from the audience.
Thank you.
All right, then we'll be back in 10 minutes. Okay, we will start again as soon as I notice that most of the panel members are back online. Okay, we are almost complete again. It seems that we already have a lot of questions waiting for us. I don't think we've ever had that many directly after the break. So there, maybe we start off with the one from Anthony Kinlock, which is a one for Michael. I can already respond. I agree with Anthony, to be honest. We will have comment on this further, Michael.
Well, I think it's a very interesting question, and I think it comes back to this question about really, is there any such thing as a mode two, given that it's really at fundamental level, it's driven by tension. So I think it really depends what you want to use it for. So from a pragmatic point of view, there are cases in industry where there may be a delamination which is largely driven by mode two, which is in the presence of compression. So how do you deal with that? A theoretical ideal G2C value is not going to help you for that. What do you do about it? So taking a pragmatic stand, then I think even though there may be some questions from a sort of fundamental theoretical point of view, then from a pragmatic point of view, the energy dissipated does increase, and therefore applying a value which depends on the compressive is potentially a good way of handling that. So I don't know. I mean, I don't know whether Tony wants to actually say something about this, and we could open the microphone if he wants to make a further comment, because I would be interested to ask him how to go about a case where we have shear and compression for delamination, given the difficulties which he's highlighted.
Okay, I will allow Anthony to talk. So I think
if he wants to, I don't want to put him on the spot. If he
yeah, but he raised his hand, so I think that is implying that he wants to.
Right. Okay.
Yes, I think you can unmute yourself and then you can speak.
Yes.
Yes, great. We hear you.
I enjoyed the overview, Michael, but I think this idea that the true G1C value depends upon the applied through thickness stresses is fundamentally wrong. Actually goes against fracture mechanics, the basis of fracture mechanics. Obviously, if you apply compressive stresses, you can measure an apparent G2C that will increase. Equally, if you applied some loading blocks and applied tension there, it would also show that the measured G1C would then decrease. Obviously, it would probably depend upon the stress state as well, which you're not doing in the measurements. But the whole idea is not to measure an apparent G1C, is to measure the true intrinsic G1C, which is a fundamental material property. And if you look at the metals people that have been dealing with these problems obviously much, much longer than certainly we composites people, their standards, while ours are vague on this, our standards say that their samples, whether it's Archon or compact tension or whatever, should be stress-free. There should be no residual stresses, and you must make every effort to minimize the stress in the sample and not go around and apply more different stresses to it. This is so they can measure a true, in their case, K1C and K2C. That's the first point, and this is very clearly stated in the metals literature and the metal standards. Now, obviously, Michael, I would agree. You have measured an apparent G2C that changes with your residual stresses, but I think that's in some ways a fundamentally wrong way to do it. You should measure the true value of G1C, intrinsic material parameter that transfers from the test sample into real life components. That's the whole basis of fracture mechanics, isn't it? That's what we teach the first year students. Having said that, your next question, of course, is a very good one. How do you allow for them? Well, what the metals people do is to measure a true K1C or K2C independent of residual stresses or other external stresses. And then what they do, of course, is when they compute, usually FE these days, compute the K1 or K2 or mixed mode K1, K2 in their samples, then this then takes account of the residual stresses, etc. So what you do always, of course, is to take, in our case, we're talking about energy release rates, we compare the energy release rate in the sample to the true intrinsic energy release rate for fracture, G1C or G2C, and the applied stresses, which may be complex, different stress states, all come out in a G1 term. So obviously the energy release rate will vary according to the applied through thickness stresses, as an example. So that's where they come in. They come in the G1 term, not the fundamental G2C or G1C term, which should be this true material parameter and measured in samples which are free from residual stresses or other applied stresses. And that's what the metal people are doing. If you go to their literature, you can see it at length.
Well, so this could be a very long debate here, and I don't want to take up the whole thing just on this one point because we've got a number of other questions. But I think I would agree with you that this is apparent G2C is perhaps a better term to use because, as I think from some of the other presentations we've heard, that there's doubt as to whether there really is a G2C in a composite. And so perhaps
I agree with those people, though. I've always been a Kevin O'Brien supporter, so I agree that this is a myth rather than a fact. But we do use G2C in our work. You've used it with Steve Hallett and all your modelling work. And the other aspect I'd note is that your modelling work and ours and many other people's works quite well if you take the G2C, as I've just explained, a true material parameter, you input that into, say, your cohesive zone model or whatever, into Abacus. But Abacus, of course, when you put all the stress states into your component, maybe it's a plate under impact, that then takes into account of how the energy release rate, G1, G2 mixture usually, depends upon the three through thickness stresses. So that's where they come in. I think in a sense, you've got them on the wrong side of the equation, if you see what I mean.
Well, I see what you're saying, but I'm afraid I don't agree. But because I think
you're in a minority, I think. Look at the metals ditch. That's what I did.
Let me just respond, and then perhaps we'll park it because I don't want to take the whole thing.
But look at metals literature.
No, just look at this transverse crack tension test, which we talk about. If you look at that test there, that's driven by the tensile stresses in the plane. And the energy release rate for that does not vary with the transverse compression. So that's a case there, I think, where it's the G is determined by the in-plane tension stresses, and the transverse compression affects the compression and therefore affects the way that the epoxy and the composite yields and damages, and therefore it affects the GC term and not the G term. So anyway, I suggest actually, while Jentel's sharing this, I would suggest we park this one and perhaps agree to differ on that in some respects. Although I think actually we're saying a similar thing.
Yeah, I think if you call it an apparent G2C, I think we're a lot of the way there then.
Well, maybe that's a good place to leave it at.
I maybe just want to add one complicating factor to this. I think what Tony mentions is correct for metals, where you can indeed get the changes in the energy release rate from just the finite element calculation that tells you what the true thickness stresses are. I'm just not sure that that would also apply that easily to composites, because when you have the true thickness stresses, your matrix is pushed further into plasticity that could change how debonding happens, how matrix plasticity happens. So I'm not sure the real or the true fracture toughness is really still the same in a just like in a metal, also in a composite. I'm not sure it's that simple. I don't think there's any real hard data on that, to be honest, but intuitively I would not immediately believe that they are the same.
But if we can't transfer our measured G2C, the true intrinsic G2C and the true intrinsic G1, if we can't transfer them from the test sample to a real life component, we're rather sort of flawed, excuse the pun, in fracture mechanics, aren't we? The whole basis of fracture mechanics is you measure on a test sample, you've got your material parameter, you evaluate the energy release rate or K1 applied, plus residual stresses, effects, etc., in your specimen, in your component, and compare the two, and away you go.
Yeah, well, I agree with you, and that's
we have a problem then. That's true, absolutely. But that's maybe the reality.
Well, that's why we adopted this approach, because we tried to apply fracture mechanics with a mode 2 delamination case, which did have transverse compression, and it didn't work. So
all your plates have got.
Yeah. Anyway, I suggest we move on.
Plates, Mike, all the impacted plates work that you've done and we've done and many others have done have obviously got through thickness compression in them,
Yes.
haven't they?
And if you don't take
Your
account of
previous
that, you get
models
the
have
wrong
worked.
delamination area
Yeah.
in the analysis.
Okay,
And
I think we indeed should close this topic, otherwise we go too long on the same topic. Giuliano, do you want to respond to this, or I don't know? You are muted.
But just wanted to make a point, but I mean, if we are closing the topic, I'll just
Okay.
avoid.
Federico, do you want to go on the same one, or
Yeah,
maybe
it's the same.
concluding remark?
Well, it's more than a conclusion of this discussion, which is very interesting. It's a general comment on something that is common not only to G2C, but also to G1C, and in fact to all properties we measure with in composite. The question to me is that which is the representativity of the value we measure in a test when dealing with the design of an actual component made of composite. And in this case, G2C is probably the most affected property by this question. And the reason for me is that mode 2 exists, is correct from a micromechanical view of the material, but happen at a micromechanical view of the material. So how micromechanical properties can represent the micromechanical processes. In my opinion, the problem here is that we have fantastic presentations about particular points of one test, how to improve it, how to trust on the result obtained. But the main thing for me is that I think we should work in the future in this sense, is to try to work on the structures where people that use the values we generate use it. In this particular case, for instance, the approach will be to try to find the value of G2C, for instance, that in an actual structure, a simple 090 laminate, provoke the damage. And I'm sure that the value we will get from this analysis does not correspond exactly with the values we have measured. And me personally, I am involved in this particular battle. And of course, I invite anyone to be incorporated to this to check the representativity of the values we get from test in the design of actual composite structures.
Okay. And now we will really conclude it. I want to go to one of the questions that's answered already, at least according to Zoom, about why no moment or rotation setups are discussed, doesn't need crack measurements. James already responded to that. Are there any other of the panel members that want to jump in on that question or answer? Not immediately. Maybe we'll leave it at the current answer. Then we jump to the next one. I think that's targeted towards Michael about the cut ply thickness exceeding 1 millimeter. Does G1C, or I guess G2C is what he means here, remain constant, or does it increase?
well, I'm not sure we have enough data to know. All I say is that graph I showed in the presentation did seem to be getting towards a plateau.
Yeah.
I think that's all I would say.
Okay. Then we go to a question of Jose towards Giuliano. It's not limited to G2C. Do you want to respond to that, Giuliano?
No, it's not limited to G2C. We've got essentially a full mixed mode implementation of these. However, I'm afraid I cannot share it. Because you are from Airbus, if I'm not mistaken, and essentially this code, this subroutine has been developed for Rolls-Royce, so we cannot use it with other industry partners. unfortunately. We are about to publish it, so it's going to be in the public domain, the algorithm, so you can work on your own implementation. It's not particularly difficult to implement. I mean, if you have an easy view, matter can be quickly adapted. But yeah, I cannot share directly what we have in Bristol in terms of code.
Yeah. Okay. Then question from Xiaodong about the use of G2C in the UD lamina. That's directed towards James. Do you see the question that we relate to, James?
Yeah, I've just read it. I think, so again, if there are cases where you have an interlaminar crack that's formed under those loading conditions, then if you can recreate that in a coupon, and that serves to be a good similitude parameter up the scale, then seems like that should be okay. But for the various reasons that we're all discussing this morning, then that can be problematic.
Yeah. Any other comments on that question, or do we close that down? Okay. Then one from
Robin Olsen. He did have his hand up. I don't know whether.
Yeah, I'm going through them in order of appearance. So then after this one, we'll get to Robin. There's a question about constraint effects on mode 2. Are there any constraint effects on mode 2? I'm not sure I completely understand that question myself.
Well, isn't the compression a form of constraint?
Yeah, that would be one.
I don't want to bring that question up again, but I don't know what other constraint effects would perhaps be helpful to clarify that question. Unless everybody else has got any comments.
Yeah. I think maybe that requires some clarification by typing in the new
with respect to
question.
adhesive joints, which I spent a little bit of time talking about, obviously there are constraint effects from the substrates, the adherent.
Yeah.
And yes, they are important, and of course they, to some extent, control the length of the process zone. So if one is trying to limit the size of the process zone or restrict how large it grows, obviously you've got the modulus and the thickness of the substrate as one sort of handle on the amount of constraint that's seen by the crack tip.
Yeah. Okay. Then the next questions are by Robin. I will allow him to talk. He should have permission now.
Can you hear me?
Yes.
Good. Yeah. Actually, I want to comment on this thing from Kevin O'Brien and others doubting that there is a mode 2, that we really have a mode 2 fracture. I mean, you have to realize that we are working at 2 levels. In modeling of fracture mechanics, we work at a sort of macroscopic level. When you talk about these coalescing microcracks, you are looking at a microscopic level. So it's true that at that level, it's mode 1. But the thing is that when we try to model it with FE or whatever, then we model it as a mode 2 fracture. And then we need a mode 2 G2C value. And I'm very surprised, actually, that both Kevin O'Brien and many others seem to have completely missed a paper by Shia and Hutchinson from 1994, which very well explains how coalescing, tunneling, microcracks in a sort of global or macroscopic mode 2 loading result in a fracture toughness, which is actually 3.1 times G1C. And that agrees very well for all, let's say, brittle and medium brittle matrices, where you get these shear hackles. On the other hand, if you have, imagine you have 2 biscuits with cream cheese in between, and you pull them apart or you shear them, then actually all is plasticity. And in that case, you see that G1C and G2C are approaching each other. So you can actually see in tests that for very tough matrices, like for example P, G1C and G2C are very close. So yeah, my feeling is that this thing with the coalescing microcracks, which are sort of microscopically mode 1, but from a sort of macroscopic modeling point of view, they are mode 2. That has been missed.
I can't hear
That's a very important paper.
Anybody wants to respond to that?
I'm looking
Yeah, we totally. Oh, sorry, Giuliano.
Go ahead, James. You go first.
Oh, thank you. I mean, we totally agree. That's the whole point. That's the whole issue we were faced with when we wanted to try to characterize a fabric tape client interface. We knew that depending upon how we oriented the stress states, we were going to get a different level of damage, different amount of damage. And so at the same time, as Robin points out, we're not modeling at the microscale, we're modeling at the macroscale. And so we either using VCCT or a cohesive zone approach or something else, in a structural FEM to model what we observe in the actual structural test as a delamination under a mode 2 driven sort of stress state. So we have no choice but to, homogenize the measurement, right? And then our job then is to determine whether or not that's a general measurement that can apply up the scale. So, and I think Kevin O'Brien was very aware of that. It's not something I think that paper, his review paper there, perhaps his opinion is set in stone from that paper, but I don't think that was lost on him.
Juliana, do you want to follow up?
No, I was about to say exactly what James said, so totally agree.
Further follow-ups on this? If not, Robin, I think you had a second question. Maybe we should explain that one in a bit more detail then.
Can you give me, you hear me again?
Yes.
Actually, when I worked at the Aeronautical Research Institute in Sweden, we normally just did ENF tests, but we also did some quite interesting buckling-induced delamination test, where you it's the opposite of this test where you have where you pull in tension, you have center crack. So basically you have a sublaminate which buckles, and then you propagate a mode or a crack by buckling. And it turns out that growth is stable, and also our FE analysis showed that it was around 95% mode 2 in that growth. So very dominated by mode 2. And we found something very interesting, and that is that for propagation, we got almost exactly the same G2C values in 0, 0, 0, 5, and 090 interface for the propagation. But for the initiation, the values for 0, 0 and 0, 5 interfaces were much higher. So actually, I think it could sort of indicate an alternative way to test specimens is actually to use 090 interfaces, because then you get a very natural, sharp initial crack, and then you get a sort of natural propagation. The problem is when you have unidirectional 0-0 interfaces is that you actually have to initiate a lot of microcracks before you can start the propagation. So I mean, that's a problem. And it's also interesting if you compare with what Shia and Hutchinson said, because they said that if your microscopic defect, they were actually developing a model for steady state propagation, but they said that if your defects are much smaller than the thickness of your sort of damage zone or interface zone, then you will get not an artificially high, but you will get a much higher value. And that's exactly what we see in tests where we have not a natural crack start. We have some sort of insert or something like that.
Anybody wants to respond to that? James?
So, I mean, in the, in D 7905, that's why we have the requirement for pre-cracked toughness measurements, for the realization that you have a damaged state in the specimen, or you, as manufactured specimens, don't have the damaged state that corresponds to a sort of naturally occurring crack under that local Mo2 loading condition. I think with respect to, if I can comment on the suggesting you go 0.90, I mean, that's going to, so the question is, do you want to test that results in contained interlaminar cracking? And if you do, then you visibly can do the 0.90 case. You just got to obviously configure your laminate so you're free of all other loading, like people are discussing, and then orient your stress state such that you would permit interlaminar cracking rather than kinking out of the plane into the 90-degree stack.
Mm-hmm.
But Robin, maybe I misunderstood. I probably did misunderstand the suggestion.
Yeah, I mean, of course, when you have a 0.90 interface, you actually, the crack sort of first deviates up through the 90-degree interface, and then it will follow the 90-0 interface. And of course, yeah, you may be right, but I thought it was an interesting observation that at least in our tests, we got exactly the same propagation values for different interface angles whenever we used 0.0, 0.5, or 90-0.
Did you look, and I assume you looked at the crack surfaces and you satisfied yourselves that you were getting similar damage in all those cases?
Yeah.
Okay.
Yes, that's right.
So your stress state was always, it could be your stress state was always such that those microcracks that we're babbling on about were always driven to the 0-degree ply in your case, right? And
exactly.
so just okay.
I'm just wondering whether Yu Gong might want to comment on that, because done work on different interfaces. Do you have any comment on that question? Optional, you don't have to respond if you don't want to. Sorry to put you on the spot.
We also test different interface of the Mode 2. We found for different material system, we may get different conclusion about how the fractal toughness change with the interface angles. Yeah, I think if we want to first, if we want to truly to understand the different interface angle, the effect of interface angle on the Model 2 fractal toughness, we should avoid the influence of the specimen fracture modelers, fracture modeling. Yeah, because when we are usually I found many study they investigate the different interface. We found the whole fracture modulus is also changed. If we really want to get the influence on interface angle, we should keep all the specimen we designed. The fracture modulus should keep the same.
I'm not quite clear what you say, the fracture modulus. Can you just clarify? I didn't quite understand what you mean.
Flexural modulus, I think. The bending modulus.
Flexural modulus. Sorry, okay. Is that what you were referring to?
And
Saying flexural modulus. Okay, yeah, good point.
Federico, you want to respond to this point? But you are muted.
Yes. I wanted to say, Robin, that I find quite coherent what he is mentioning. And the reason is, again, the representativity of the value we get from the test when we apply it to a certain structure. We found, for instance, for G1C that you get from DCB, a DCB test, we find a value. Now, when studying the propagation, the onset and propagation of a crack in a laminate, the value we obtained was much higher. And the reason is that the micromechanism or the mechanism of damage in a test at micromechanical level are completely different to the mechanisms of damage at micromechanical level in an actual structure. For this reason, we have to continue working on the improvement of the test and studying the results. But at the same time, I think we need to enter into the connection in between the state of the test and the state of a real structure at the level of the mechanism of damage that originate the failure.
Okay. Yeah, I think this problem of different interface angles has been a long-standing issue, and it's very difficult to come to real strong conclusions that everybody can agree with. I think that's also clear from this discussion we're having now. Okay, I think we should close that topic now. Then we move on to the question of David Brearley about whether G2 depends on compressive stress or strain. We kind of already addressed this, right?
I'm wondering, is that question about G2C? I mean, that's really related to this debate we had a while ago, I think, isn't it? I'm not sure there's a separate point there. And hydrostatic sensitivity is very important, and yeah, I think that's one of the reasons why we see changes in behavior with through-thickness compression.
Yeah, Federico, or you still have your hand up from earlier, perhaps?
No, I don't understand very well there.
Giuliano, you want to respond?
Just because it has been raised again, but just to make a point, even if we consider classical fracture mechanics and you consider a mode 2 crack with friction and so with a compressive force, so effectively the presence of that compressive force with friction, linear elastic fracture mechanics changes the order of the singularity at the crack tip, and so it also changes effectively the mode 2 fracture toughness if we calculate it back from with the Irvine integral. So and that is very well known, and that's why the standards for metals dictate the coupons to be stress free. But also another point about linear elastic fracture mechanics, we invoke it, and we also think about stress intensity factor. But if we want to use it also in composites, we should be considering the role played by the T stress, which could be very, very significant also in mode 2.
Yeah. In the meantime, David also confirmed in the chat that this question has been answered indeed. Okay, then we move to the question of Torquato Garulli about the possibility of having plasticity and damage in the specimen arms or in the adherence, and what effect that would have on GC or JC. Anybody who wants to go first on that one?
I
Yes,
think
Michael.
Professor Kinglock replied to that.
Yeah, yes. Michael, you want to go further on this? Michael May. Sorry, just to be
No, I
specific.
was just saying that Tony Kinlock has perfectly answered that question. So if we want to do linear elastic fracture mechanics, we cannot allow any damage or plasticity in the arms. That would make just the test invalid.
Yeah, I would also agree with that.
Yeah.
Okay. I think then we have gotten through the open questions right now. Are there any other questions either from the audience or from the panel members to each other?
Well, perhaps I can ask a question to Bamba. So we did some ELS tests, and we found that the test was not stable. So, I mean, according to the papers, if you have the right parameters, you should get a stable propagation. But for our test setup, for I'm not quite sure what reason we didn't. Is this a well-known problem? Have you got any comment on that?
Yeah, I can comment. So, so there are stability criteria.
Yeah.
So each one of these coupons has a different ratio of A over L naught, which would suggest stability. Obviously, they're typically applied to uncorrected crack lengths, and some materials are inherently more unstable than others. If we think about the DCB, for example, the DCB is notionally a stable geometry, but we all know that we often have stick slip and instability in DCB specimens. So there's always a problem, and we're always a little bit disappointed when we don't get stable crack growth, because we want usually to develop compliance functions and then use that to do other things. So I do agree that the ELS doesn't always give us stability, and we normally try and work around it. One thing that we wrote into the test standard was to help with the stability of the test. You can obviously do a pre-cracking with a shorter span length. So one thing you can do is, of course, use a very much shorter span length to pre-crack, and then increase the span length. And that often is very successful in subsequently getting a stable delamination. So often you'll get instability from the insert. So some sort of pre-cracking is usually good. Of course, it doesn't help if in the pre-cracking it cracks to the end of the specimen.
One of the problems with that is.
So in the ELS, you can avoid that by clamping at a relatively short distance, so that you effectively pre-crack into the compressive region around the clamp, and the crack stops. So yeah, I think but I do agree. Yeah, we've seen the problem, and there are workaround solutions to it.
Thank you.
There are now more questions. One is about strain rate, so I guess mainly for Michael May in this case. Can you read through it and try to answer it?
Ooh, that's a tough one. In principle, what you can say is that going for high rates should give you similar behavior than going to very cold temperatures. So we are seeing that when you want to do testing, even static, at very low temperatures, say ZAP minus 150 degrees C or something like this, you're running into all sorts of problems, like your I've seen some results from Hamburg, for example, where they have a very nice frozen DCB specimen. So you need to solve all sorts of challenges, in particular if you want to have like an optical measurement of your crack tip, propagation, So I think things there still require a lot of research to be done. And in particular, if you want to do then compare like a high rate at quasi zero Kelvin, this would make life completely erratic.
Yeah, good luck with that.
So, but we're trying to go for this. Actually, we are writing a proposal at the moment.
This sounds like a very interesting area to pursue. I'm thinking about the work of Mayano and applying the time temperature superposition principle, which he's shown for many cases does allow a good comparison by changing the temperature or the rate or whatever. I don't know. Yeah, I think that would be something very good for further research, I would think.
I perfectly agree.
Any further comments or responses to this one, or do we move to the next one? Oh, okay. We move to the next one. This is about natural fiber composites in ENF test showing nonlinear force displacement curves. I can comment on this, as it obviously comes directly from the nonlinear response of the natural fibers. Most of them are not linear. If you load them in bending, they even have a different modulus in tension versus in compression. So there's all sorts of weird effects that do make data reduction and applicability of linear elastic fracture mechanics significantly more complicated. Any other comments on that question?
You know, you can circumvent it possibly by just going with J, right, rather than G. So you haven't circumvent you having to make the assumptions that one needs to make when calculating G. But obviously it depends the source of the nonlinearity, is it? Yeah, so I'll leave it at that.
Further remarks on that question?
Maybe you could also think about using backing beams, sort of stiffening the relatively flexible substrates or arms that you're using, which might improve the situation.
I think that's also a good suggestion indeed. So I think we're now again at the end of our questions. Any further points of discussion? We've already gone through a lot of questions. Giuliano.
Yeah, this is a question primarily for Bamber, I would say. But clearly there is a huge demand from industry about testing standards that can be applied at temperatures different than room temperature. And traditionally in industry, they consider the hot, wet scenario to be the most relevant or the one that gives the largest knockdown for material properties, which is not necessarily true. So I'm wondering whether there is any consideration towards extending testing protocols to a broader range of temperatures in particular.
Yeah, I mean, yes. We certainly talked about it, but we haven't actually initiated within the ESIS group any high temperature testing capability. We've obviously looked at the fracture mechanics. We've looked at alternative ways of obtaining G. But yeah, I think it's a very good suggestion. And if there are groups interested in collaborating in these activities, we're always very eager to hear and potentially set up a new work activity in the area. But we don't currently have anything on performing fracture mechanics in at a higher temperature. We do have environmental stress cracking activity where polymers are tested in liquid environments, usually via a constant load SCNB or compact tension type of loading arrangement. But I think temperature is a very good suggestion and would be worthy of future activity. So yeah, if anyone would like to get involved and yeah, participate, we'd very much like to hear from them. So including Bristol and
Even if I don't believe in mode 2 fracture toughness, I'm joking. But no, I think it's extremely important because also today we're talking about mainly about organic matrix composites, polymer-based composites, but clearly, I mean, this is extremely important, for example, for ceramic matrix composites. And also for organic matrix composites now with the push towards hydrogen economy, whether will continue or not, we will see. But there is a lot of interest in, a renewed interest in cryogenic properties of composites. So,
yeah, agreed.
Can I just ask James if there's any comment from D30 and activities in the US?
There's yes, but it's for hypersonics applications, so I'm not permitted to talk about it. D30 doesn't at this time. C28, I think, is the ceramics matrix composites guys in ASTM. I'd chat with those guys. But my guess is any questions going to be met with silence. But be worth some bit, yeah.
I see there's a hand from Tony. Go ahead, you can unmute yourself. You should still have the permission.
Sounds nice to see and hear from James after many years. In TC4, led by Bamba, of course, these days, we're doing a lot of emphasis on fatigue, which you've probably seen, and doing fatigue, and particularly getting the classic DAEDN versus, in our case, strain energy release rate. And lots of problems still, even though we've been working on it now for 25 years, I think is the length of time we've been looking at this problem, trying to get a standard out. Really, the question is, ASTM, are they similarly like us struggling, or have they given up trying to get a standard out for getting DADN versus delta G, or getting, versus strain energy release rate?
Yeah, so I'm glad to hear that your length scales are like ASTM style too. So yes,
I think we're almost there though.
Okay, good. Yeah, we do. We have so as you know, we've got 6115, which is onset.
Yes.
We have a work item for growth rates, and that is very close to becoming a standard, and that's for mode 1. So a couple of things that we're looking at are, control modes. So that the typical options for doing constant amplitude load, constant amplitude fatigue, but also G control. And so we're working on incorporating, for instance, a method actually using J integral. So since we can instantaneously measure J, then using J as a method for controlling fatigue tests to get a G control. So we have lots of our industrial partners wanting G control type methods for various material systems. So yeah, that's along the lines we're working, and I'm happy to share the work item for the growth rates proposed standard that we've got coming up. And I'm sorry that you have to ask the question, and again, it's on us. I blame myself for not being as communicative as we should be. So thanks for the question, Tony.
Well, maybe liaise with Bamba particularly, because we've got a draft standard. Well, it's a draft standard published within our group, but it is referenced in various pieces of open literature, so it is available to everybody. But we've got a draft standard for doing such measurements, and also talking about the interpretation of the data. And the round robin seems now, which we've now embarked upon, seem very encouraging. This is then led by Bamba, Andreas Brunner, and René Alder-Lestin Delft. The worrying thing, really, this is a different subject, but one worrying thing to say to people is it really shows that most of the fatigue data, like DADN versus delta energy release rate in the literature is probably not worth the paper it's written on. Most of those results are probably not accurate. And we've seen this from the round robins, which we think we can now explain. But there is a draft standard out now from the TC4 ESIS committee, which I'm sure Bamber and Bruno and René Alderleston you can liaise with, James.
Yeah, thank you. Yeah, it would be great so we take your lessons and don't waste time at the very least. So yeah, I appreciate that. Thank you.
The essence of the problem, as a simple statement, is where you get fiber bridging developing when you do the fatigue crack growth, and that can completely, obviously, as you might guess, especially with a typically mode 1, it completely throws off the fatigue crack growth curve that you get. You get a whole series of fatigue crack growth curves depending upon how much fiber bridging you developed before you started your fatigue test. And since if you look through the literature, people start their fatigue test, there's no standard, so people just start them after 1 milliliter, 5, 10, 20, etc. And therefore there's this whole range of fatigue crack growth curves. And unless you control that, you've got no idea where you are. But I think Bamber and his committee have got hold of this now, and hopefully going to take it forward to an ISO committee.
I'll shoot you an email, Bamber. Thanks, Tony.
Super. Yeah.
Appreciate it.
We got a meeting. Our next meeting actually probably will be in Madrid in September. So we'll make sure.
Great.
I don't know whether you're going to be in Europe around about that time, but we'll let you know. But
Thank you.
We'll stay in touch anyway.
Great. Thank you.
Okay. I think we are reaching close. Sorry. Go ahead, you. Go ahead.
Hi, James. I have a question. You talk about the D6115 the onset mode 1. So I know the judging criteria for the onset of mode 1 delamination is the increase of the compliance. They give 0.01 or percent 1% or 5% compliance increase for judge the compliance onset. But I think the 1% is very small, which is easily to be affected by many factors. So what's your opinion about this?
Yeah,
5%. Yeah.
Yeah, I don't like the compliance change as a criterion because it's structural, right? So you, depending upon the thickness of your laminate, and there's a range of laminate thicknesses in the standard, means that compliance change corresponds to a certain crack length change. I would prefer if we had a more general criterion to relate to onset. So I think you bring up really good points. One way to do it is to assume onset occurs after a certain amount of delamination growth, if you like, and then back calculate what the necessary compliance change would be given your specimen. But I certainly see there are issues associated with going along that path as well. So yep, I'm glad you bring it up. It's a good point. And I'll let anybody else chime in who's probably got way more educated response than I do on that. So thank you for bringing it up.
Thank you.
Sorry, any follow-ups on that? Is there maybe a final question or some concluding remarks on the overall workshop, Federico? You are muted.
Okay, it's a question for the audience. So I'm a bit surprised that the word ultra thin plies has not been mentioned today. And why we have not mentioned this? It's because we think that we don't work on this topic, or we think that the thickness of the ply does not affect the value of G2C. It's just a reflection on this, if you have anything to say about it.
Well, I would argue it's perhaps not so much the ply thickness that affects this? Because in principle, if it's a material parameter, which we've had some discussions on, it should not matter. But of course, what does change is the microstructure. They do not have the same degree of fiber packing. They have different degrees of misalignment. So I think those parameters can affect mode 2 and mode 1 fracture toughness. There is some data on this in the literature. I don't remember the exact conclusions, but I think it's the microstructure that can affect the property a bit.
I think another.
Sorry.
Go ahead, Federico.
Oh, sorry. You said it's a material parameter. The problem is that we use these for predicting the delamination in between two laminas of a laminate. For instance, it's reasonable to use it. And I'm convinced that this delamination in the laminate is affected by the thickness of the laminas involved, which goes again to say that, is it a material property or not? Probably not. Sorry.
Michael?
Yes, I was going to comment on the importance of the effect of how much resin layer there is on the surface of the ply, which may also depend on the ply thickness. But it has been shown very clearly that increased resin improves the mode 2 fracture toughness. And that's one of the reasons, not the only one, but one of the reasons why these interlayer materials have higher fracture toughness.
Hmm.
I think Robin also wants to respond to this.
Yeah. Do you hear me?
Yes.
Yeah. I mean, of course, it's also always important with the microstructure and so on, but I would say that the ply thickness should be much more important for mode 1 growth than for mode 2 growth, because the sort of the size of the zone where you have micro damage, it's it could easily extend quite far above the crack plane if you talk about mode 1, but mode 2 growth is much more needle shaped process zone. So I would think that of course it could matter, but I would say it's more important for mode 1 than for mode 2. And I guess the only way is to measure it simply and study it. It could be worth trying, but normally when you look at these sort of these shear hackles, the size of them, it's usually they are very small. It's just of the same size as the distance between fibers. So I wouldn't think that the ply thickness is that important. I mean, you have another thing in the whole laminate, and that is if you get sort of widespread microcracking in your specimen. And that's, of course, can affect results, but that's actually something you can eliminate if you use J evaluation methods, J integral methods, instead of just looking at G. So yeah, you need to, and I think that's the main reason why we see different results from multi-directional laminates, is that we get widespread microcracking in our specimens.
Robin, my intuition is similar to yours. Similar. And also I agree with Michael. The problem is that I think it's something that we have to do sometime to check that this is okay. Because in many previous occasions, my intuition was not correct.
And just to be clear, I think the people at EPFL have actually measured this for different ply thicknesses, both in mode 1 and mode 2. And I think it's correct that in mode 1 it has some effect, and in mode 2 it doesn't. I just don't remember by heart whether there was a difference between initiation and propagation values. But it was not significant in mode 2, as Robin is correctly suspecting, I think. Any further responses to that topic? No? Are there perhaps any concluding remarks on everything we've discussed so far?
I'd like to make a comment about your next year, you mentioned mode 3, and at least for tape composites, I think, you know, we have obviously an important relationship between what to expect under mode 2 loading conditions and mode 3 loading conditions. So I hope that it's if I were to participate next year, I would be trying to consider implications of, you know, stress state, the role in stress state orientation relative to your material orientation, and that probably encompass just the sheer loading conditions rather than distinguishing out mode 2 and mode 3. Of course, yeah. So I think there's an important kind of distinction or relationship between the two that's at least in the standardization community we've been trying to sort of keep separate because for the obvious reasons. But anyway, so just maybe consideration for you guys for next year. If you're going to talk about mode 3, it shouldn't just be out of context of mode 2. There's an intimate relationship between the two and maybe a more holistic consideration of those things. Anyway,
yeah, I do not disagree with you, James. It's a very good point indeed. Yes. Any further comments?
Well, I think we've had a really good discussion. I think it was a lot more lively this time than perhaps the last one we had on mode 1, which perhaps reflects the fact that there are more questions and complications with mode 2. So I think it's been very interesting, the debate about, well, is there a mode 2 at all? Is it a myth or not? And the question about what scale we look at the problem and what we want to use it for. And perhaps we should, in some of these cases, we should be using an apparent G2C rather than really calling it a material property, because as we've seen from the presentations, it depends on a lot of different factors. The whole issue about the tape versus fabric, the huge process zones that we sometimes see, there's a lot of complications there. So I think there's clearly more research that needs to be done. But I think, and as Federica was also, I think, saying, is we should be orienting this towards, well, what are we going to do with it? How is the industry going to be able to use this and actually help to drive things forward? So yeah, I'll thank our panel members for some very interesting points and some good discussion, and for our audience as well for giving some good questions.
Yeah, and maybe also just a suggestion. We haven't started planning the one on mode 3 and mixed mode yet, but if you think you have a good topic to present there, or if you have suggestions for speakers, they're always welcome. You can send it to any of the 3 of us, and we will then consider them as speakers for the next workshop. That makes our life easier, so they're definitely welcome to do that. If there are no further questions, we can conclude here. We are finishing about 15 minutes early, which is fine. I think we have very thorough, very good discussions. We will upload the recording somewhere roughly in the coming week or so, and then once that is ready, we will share the link with you, including all the presentations. I think I've received the presentation from most speakers already, but I think there's maybe 1 or 2 still missing. So I will follow up with those or send them right away. Then we have them available to share with all the audience members once the recording is available as well. Okay. And thank you very much to our speakers and to our audience for engaging in the discussions, and we'll see you at the next workshop.
Thank you.